Hi everyone. So in this paper, or in this video, I'm going to go through the January 2012 paper, which is the first mock that you did. So the first question is on metal extraction, and it's basing the question on a metal that you haven't come across before, but it is likening it to titanium. So sometimes the questions will ask you something that perhaps you haven't learned specifically, but will be related to something you have learned. So here it says that the silicon chip industry requires the production of pure silicon. Silicon is extracted from its ore, silicon dioxide, SiO2, by a process similar to that using the extraction of titanium. Write an equation for the formation of SiCl4 from SiO2 using chlorine and carbon. Now you'll notice that both of these are the reactant and product for the first equation, the extraction of titanium. It's just they've replaced titanium with silicon. So the equation here is SiO2, you need carbon, and you need chlorine, which you need to remember is Cl2, and that makes your silicon chloride. And it'll also make either carbon monoxide or dioxide, and which one you choose will affect the numbers you need to put in front of these to balance. I'm going to choose carbon dioxide because that means I only need one carbon, but I do need two chlorines to balance that equation. And it says suggest how the liquid SiCl4 is purified. Now this isn't asking you how the silicon is extracted from that silicon chloride, it's just asking you how the liquid silicon chloride is purified from this equation. And whenever it's liquid, then it's distillation that will purify it. If we move down, the final stage in this extraction of silicon involves the use of hydrogen gas to convert the silicon chloride into silicon hydrogen chloride. Write an equation for this reaction. Now, a lot of you fell down on this question just because you forgot what hydrogen chloride, or the formula for it was, and it's just hydrochloric acid, and also you need to remember that hydrogen gas is H2. So you're going to make your silicon, and you're also going to make HCl. So a few of you wrote HCl2, it's just HCl, and to balance this, you need 4 HCl and 2 hydrogens. State the role of hydrogen in this reaction. Well, the role of any of the other things when you're extracting a metal is a reducing agent, because you're always reducing the metal from a positive oxidation state to an oxidation state of 0. So whenever it asks you for the role of something in an extraction of metal question, it is always a reducing agent. Give one risk associated with the use of hydrogen gas. Well, we know that it's very flammable, or it burns easily, but I would prefer you just to put explosive, because if you say it burns, you must say it burns easily, because a lot of things burn, but not everything burns easily. Yeah. The magnesium used to make magnesium ferrosilicon alloys is extracted from magnesium oxide using silicon. Write an equation for this reaction producing magnesium and silicon dioxide. Now, if you look to the top of this question, you'll notice that they show you what silicon dioxide is, so you shouldn't be getting that formula wrong. So it's going to be magnesium oxide, which you should know from your group 2 work as MgO, plus silicon, and this makes silicon dioxide plus magnesium, and to balance this we need 2 Mgs and 2 MgOs. Now I've actually been a bit careless here, and I've drawn my M's with curly tops, and I'd rather you were writing your M's with pointy tops like that, so it's obvious it's a capital letter. A few of you were drawing it like that, and you would lose marks for that. You need to make sure the first letter is a capital, second letter is a small letter. This next question was an Equilibria question, specifically a bit later on Le Chatelier's principal question, but this first question just asks you to give 2 features of a reaction at equilibrium. Now, a reaction at equilibrium, the question is the same as defining a dynamic equilibrium. First feature is that the rate of the forward reaction equals the rate of the backward reaction. Now, a few of you knew this but didn't really write down the right thing. A few of you put the forward reaction equals the backward reaction. You're not saying what about the forward and backward reaction equals each other, so you need to be specific about what you're talking about. And the second thing is about the concentrations of the reactants and the products. and they do not change. So the concentrations, and you can't just put concentrations do not change, you need to say what of. So concentrations of reactants and products do not change. If we move on, explain why a catalyst has no effect on the position of this equilibrium. So a catalyst speeds up a reaction, but it speeds up both the forward reaction and the backward reaction by equal amounts. So to get both of these marks, the first thing you've got to say is a catalyst increases the rate of reaction, the rate of the forward and backward reaction. And after that you've got to say by the same amount. Or you could say a catalyst increases the rate of the forward and backward reaction equally. So the 2 marks, if we're saying it increases the rate of forward and backward reaction, the second mark is saying it increases it by the same amount, or both of them equally. For this next question, we are going to need the equation for the Haber process from the last page. I'm just going to put that at the top here. So it's N2 plus H2 is in equilibrium with NH3, and to balance that we need 2 NH3s and 3 H2s. So look at the question. It says, use a diagram to state the effect of an increase in pressure at constant temperature on the yield of ammonia. Use Le Chatelier's principle to explain this effect. So you can see that pressure is along the bottom, and as I increase the pressure you can see the lines all go up. They do flatten near the end, but they're still increasing as I increase the pressure. So the effect on the yield is fairly obvious. The yield increases. And the explanation is always the same order for when you're talking about pressure. And the first thing to state is how many moles of gas are on both sides of the equation. So you'll see that the left-hand side of the equation has 4 moles of gas. The right-hand side of the equation has 2 moles of gas. So that's the first thing you'll say when you're answering a pressure question. So the left-hand side has 4 moles of gas, and there are 2 moles of gas on the right-hand side. That's your first mark. Second thing is to say, therefore, the equilibrium shifts or moves to the right-hand side in order to oppose the increase in pressure. Now, a few points to make about this. First thing is that you have to say the equilibrium is shifting. Never say the reaction shifts or it shifts. You have to state the equilibrium shifts or moves. You can't say goes. You've got to use one of those words and say which side it moves to. And then in order to oppose, not the change, but state what the change is. So here it opposes the increase in pressure, which it tells you in the question. This next question requires the graph again, which you should have in front of you. And it asks you to use a diagram to state the effect of an increase in temperature at constant pressure on the yield of ammonia. Usually Chatelier's principle explains this effect. So it's temperature this time we're increasing. And you'll notice on the graph that as we increase the temperature, the yield goes down. And so the effect on the yield is it decreases. Now that means that the reaction is shifted, sorry, not the reaction, the equilibrium is shifting to the left-hand side with an increase in temperature. Which means the backward reaction must be endothermic. Which means the forward reaction must be exothermic, and whenever you're talking about temperature in Le Chatelier's principle, you must state what the forward reaction is first. So forward reaction is exothermic. Usually you can deduce this from a delta H value, but in this case you couldn't. You just had to work it out based on the fact that an increase in temperature was decreasing the yield. So forward reaction is exothermic, therefore equilibrium will shift to the left-hand side because the yield is decreasing in order to oppose not the change, but what the change is to oppose the increase in temperature. We move on. An equilibrium with a pressure of 35 megapascals and a temperature of 600 Kelvin, the yield is ammonia 65%. State why industry uses a temperature higher than 600 Kelvin, and this is to increase reaction rate. Don't say what a compromised that it's a compromised temperature, say why it's a compromised temperature. So here it's increasing the reaction rate. And state why industry uses a pressure lower than 35 megapascals, do not include reference to safety, so it's to decrease cost of the equipment used. So never say that it's cheaper, say why it's cheaper. So say what is cheaper essentially. So that would suffice for that 1 mark. This next question is a kinetics question. So it says, the diagram below shows the Maxwell-Boltzmann distribution of the molecular energies in a gas at 2 different temperatures. There it is. On one of the labels of axes, so one of the axes is labelled, so that's energy there. Complete the diagram by labelling the other axis. So the other axis is number or proportion of molecules, not particles. You must say molecules. And then state the effect, if any, of a solid catalyst on the shape by these distributions. Now, remember a catalyst, so here is the activation energy without a catalyst. With a catalyst, it's here. The shape of the actual curve, the distribution, does not change. Merely the activation energy changes. So here you can say no effect. I know it gives you a lot of space there to write that, but don't be put off by that fact. Then it says, in the box, write the letter V, W, X, or Y that represents the most probable energy of the molecules at a lower temperature. Now, remember, remember that the lower temperature is the one with the higher peak. So this one is the lower temperature that I'm drawing over now with the blue, and the higher temperature is this one with the red. So the most probable energy of the lower temperature is this peak up here. So the energy of that peak is X. V is the number of molecules, that energy. X is the actual energy of that peak. So in that box we should write X. And finally, explain what must happen for a reaction to occur between molecules of 2 different gases. So the first thing they must do is collide, and the second thing that must happen is they must collide with enough energy. Now, a few of you are writing that they must collide in the right orientation as well. That is true, but these are the most basic things first that must happen before we really think about orientation. This last question on kinetics says, explain why a small increase in temperature has a large effect on the initial rate of reaction. And I think this is in bold on your flashcards, that the fact you need the first word to be many. So many more molecules have an energy higher than the activation energy, higher than. And you can write EA if you want for activation energy, but if you can't remember what the symbols are, then always write it out fully. This next question, question 4, is a few different topics kind of merged together. We've got a bit of extraction of metals, we've got a bit of Hess's law, a bit of redox. So we'll start from the top. Iron is extracted from iron 3 oxide using carbon at high temperature. Say the type of reaction that iron 3 oxide undergoes in this extraction. So remember, the metal is always getting reduced, so this is reduction. The iron is getting reduced from iron 3 plus to just iron metal, which has an oxidation state of 0. Write a half equation for reduction of iron 3 ions in this extraction. So you've got iron 3, remember the 3 represents, it's got a 3 plus charge on it. You're going to add 3 electrons to that to make your iron. Then it says at high temperature carbon undergoes combustion when it reacts with oxygen. Suggests why it is not possible to measure the enthalpy change directly for the following combustion reaction. So remember that when you're burning something, if you put something on, for example, if you put the Bunsen burner on a yellow flame, that is incomplete combustion, but you're not going to make purely carbon monoxide, you're going to make carbon dioxide as well. And that's the reason we can't measure the enthalpy change for this reaction directly for combustion, because some carbon dioxide will be made too. Next question, state Hess's law. Simple definition, or rather two definitions here. So it's Hess's law. First is the enthalpy change. Must write enthalpy change, not energy change. The enthalpy change is independent of the route taken from reactants to products. Then state the meaning of the term standard enthalpy combustion. So again, the enthalpy change must be enthalpy when 1 mole of a substance is burned completely in oxygen with all reactants and products in their standard states. Then we have a Hess's law question, which was done fairly well by most people. The main mistake that was made by people were either the arrows were going in the wrong direction in the first place, or actually quite a lot of people forgot to times this number by 3. So what you should have had are the arrows going up first, because these are all formation enthalpies. So we've got an arrow going up to each of these. And you've got Fe2O3, which is minus 822, so put that on the arrow to begin with. You've got 3 carbon monoxides, each minus 111, so that's going to be minus 333 overall, because you're going to times that by 3. 2 times plus 14 for the iron, so that's plus 28. And then 3 times minus 394, which is minus 1182, I believe. The arrows that are going to be swapped are the first two, because we've got to go from this side to this side via the middle. So this side's got to go down to go back up again on the other side. So we're going to swap over these two numbers. So this is going to go down instead. We're going to have a plus rather than a minus. Then we've got to add all those up. So what we've got is delta H equals 822 plus 333 plus 28 minus 1182, and that should equal plus 1. That's going to be kilojoules per mole, but you generally don't get a mark for the unit, so you can leave it as just plus 1, unless they ask you for the unit. Write an equation for the reaction that represents the standard enthalpy of formation of carbon dioxide. So this is going to be C plus O2 goes to make carbon dioxide, CO2. So what you've got to do here is just follow the definition. So standard enthalpy of formation is the enthalpy change when 1 mole of a substance, so that's the CO2, 1 mole of it, is formed from its elements, so these are its elements, with all reactant products in their standard states, and that's the last bit. You've just got to add state symbols to show these in their standard states. And then finally, state why the value quoted in part C for the standard enthalpy of formation of CO2 is the same as the value for the standard enthalpy of combustion. And that's just because the standard enthalpy of formation is C plus O2 goes to CO2, and the standard enthalpy of combustion of carbon is C plus O2 goes to CO2, and so therefore they are the same reaction. This next question is a redox reactions question. First thing is working out oxidation states. Now, you've got to work out the oxidation state of iodine, I2. Remember, the oxidation state of any element by itself is just 0 by definition. And this next one requires you to work out the iodine HiO3. Remember, each of the oxygens are minus 2, so that's going to be minus 6 overall. The hydrogen is plus 1, and it's going to add up to the charge on the molecule, which is 0 in this case. So iodine must be plus 5, because plus 1 plus 5 minus 6 equals 0. Then we've got to balance the following equation, and this just requires you to take some time, I suppose. So you're going to have 2, 10, 4 if you balance this. If you don't balance it straight away, then leave it and come back to it, because it's only worth 1 mark. It's not worth your time wasting on it. And the last question on this page is a redox reaction question. So basically it's asking you to combine these two equations to give the overall ionic equation. You'll notice that there are 5 electrons in this top equation, but only 1 in the bottom. So we've got to multiply the bottom one up by 5, so the electrons cancel. That's going to turn into 2.5 and 5 electrons. So we add them together, so you've got IO3 minus plus 6H plus 5I minus goes to make 3H2O, and then you're adding together 2.5I2 and half I2, so that makes 3I2 overall. And then the oxidizing agent here is a thing that gets reduced itself. Remember, reduction is the gain of electrons. So all you've got to do is look at these two reactions and see which thing is gaining electrons. Now, if something is gaining electrons, then the electrons are going to be one of the reactants. They're going to be added to the thing. So here, IO3 minus is gaining electrons, so that is your oxidizing agent. Then we get onto some halogens work. So we've got, when concentrated sulfuric acid is added to potassium iodide, solid sulfur and a black solid are formed. Identify the black solid. So the black solid is going to be the thing that comes from the iodide. Remember, iodide is going to be oxidized to iodine. If it just says identify something, then always write out the words. Unless you know the formula and don't know the words. Always write out what you definitely know. Because if you just wrote I for iodine, that will be wrong, because the iodine you see is I2. Then it says deduce the half equation for formation of sulfur from concentrated sulfuric acid. So we're going from sulfuric acid to sulfur. So balance sulfurs first, already balanced, then balance the waters by adding, balance the oxygens by adding water to 4H2O. Then balance the hydrogen. So we've already got 2 here. We need 8 overall, so we need 6H plus, and we also need 6 electrons to balance the charges. So that's that. And then we have, when either ions react with concentrated sulfuric acid in a different redox reaction, the oxidation state of sulfur changes from +6 to -2. The reduction product of this reaction is a poisonous gas that has an unpleasant smell. Identify as gas. The gas is hydrogen sulfide, that's the one that smells of egg, or H2S. Now, some of you wrote SO2 for this, and really that shouldn't have happened because it's told you that the sulfur has an oxidation state of -2. And in SO2 it has an oxidation state of +4. Here it has an oxidation state of -2. Remember, each of the hydrogens is +1, therefore the sulfur must be -2. A yellow precipitate is formed when silver nitrate solution acidified with dilute nitric acid is added to an aqueous solution containing iodide ions. Write the simplest ionic equations. That's just writing the ions that are reacting. So the two ions that are reacting are Ag plus and I minus, and that makes AgI. The nitrate is just a spectator ion that doesn't really react. Stays in solution and therefore stays as an ion. State what is observed when concentrated ammonia solution added to this precipitate. Well, remember that silver iodide doesn't dissolve in either concentrated or dilute ammonia. Silver bromide dissolves in concentrated and silver chloride dissolves in dilute and concentrated. So here you'll see no visible change. If nothing happens during a reaction, you won't see anything. Use the phrase no visible change to explain that. And then state why the silver nitrate is acidified when tested for iodide ions. That's to remove any ion that might form precipitate with the silver nitrate. And the ions that would do that primarily are carbonate and hydroxide ions. So here I'd rather you were writing to remove carbonate ions. Or you could put hydroxide there instead. Don't put both, just in case you spell one of them wrong or get one of them wrong. And a bit more halogens and redox. We've got consider the following reaction in which iodide ions behave as reducing agents. Cl2 plus 2I minus goes to I2 plus 2Cl minus. In terms of electrons, take the meaning of the term reducing agent. So reducing agent is being oxidized itself, so it's being losing electrons, so it's loss of electrons. Or you can say the reducing agent gives electrons to something else, or donates electrons to something else. Don't say a pair of electrons, that is incorrect. It's just electrons plural. Write a half equation for the conversion of chlorine to chloride ions. So chlorine is your reactant into chloride ions. So chloride is Cl minus, chlorine is Cl2. So you need 2 Cl minus and 2 electrons on the left-hand side. And then finally, state why iodide ions are a stronger reducing agent than chloride ions. So when things are reducing agents, they're being oxidized themselves. So that means they're losing electrons. And the reason why iodide ions are better at doing this is due to their electron structure. So chlorine has 3 shells, whereas iodine has 5 shells, okay? And the electrons that are being lost are the ones in the outer shell. So the electrons in iodine, or iodide ions rather, are going to be lost more easily because they're less attracted to the nucleus. And so what you'll say here is that there are more electron shells in iodide ions, and so electrons are less attracted to the nucleus, and so are more easily lost. Okay. So next, the table shows the structure names of 3 compounds with MR 72. There they are. Explain why MR values measured to 5 decimal places cannot distinguish between compounds 1 and 3, but can distinguish between compounds 1 and 2. So the MR values won't distinguish between compounds 1 and 3 because they'll be the same. But you've got to say why they'll be the same, and really this question is a bit stupid because it seems so obvious. The reason why 1 and 3 will be the same is because they have the same molecular formula, the same number of carbons, hydrogens and oxygens. So compound 1 and 3 have the same MR as they have the same molecular formula, and compounds 1 and 2 have different MR as they have different molecular formula. It's as simple as that. And then a simple chemical test using either Fehling's or Tollens can be used to distinguish between compound 1 and compound 3. Choose one of these 2 reagents and state what you'd observe with each of the compound 1 and compound 3. So compound 1 here has a CHO on the end and his name is butanol. So from that you can work out that it's an aldehyde. Compound 3 is butanone and therefore is a ketone. So I'll choose Tollens first, so Tollens reagent. And compound 1 is an aldehyde, so it would be a silver mirror you'd observe, and no visible change with compound 3 as the ketone. And if you chose Fehling's solution, then compound 1 would be a brick red precipitate, and compound 3 would still be no visible change. Next question is a bit of group 2. So group 2 elements and their compounds have a wide range of uses. Parts A1 to A3 draw a ring around the correct answer to complete each sentence. So first, what happens to the solubility of the hydroxides? Well, remember barium hydroxide is extremely poisonous because it dissolves so much, and magnesium hydroxide doesn't really dissolve that well, and so the solubility must increase down the group for the hydroxides. The first ionization energy will decrease because the outer electrons are going to get further and further away from the nucleus, and therefore is less attracted to the nucleus, and so will be more easily removed. And the atomic radius, there's more and more shells, therefore the atom gets wider. And then explain why calcium has a higher melting point than strontium. Well, strontium is lower down in the periodic table than calcium. So calcium has less shells of electrons, so it's a smaller ion. And then, therefore, the attraction between the delocalized electrons and the ions is stronger. Or you could actually say, I think for this mark, you could just say therefore it has stronger metallic bonds. Acidified barium chloride solution is used as a reagent test for sulfate ions. State why sulfuric acid should not be used to acidify the barium chloride. That's just because sulfuric acid contains sulfate ions. And then write the simplest ionic equation for reaction that occurs when acidified barium chloride solution added to a solution containing sulfate ions. So barium is Ba2+, sulfate is SO4 2-, and what that makes is BaSO4. Now a lot of you knew this, but for some reason wrote Ba plus S and missed out the oxygens. So try and be a bit more, have a bit more common sense when you're trying to work these out. If you know BaSO4, then it makes sense to split it in the middle to get Ba and SO4. Now, maybe you wouldn't know the charges, but it's inexcusable really to write an equation that doesn't balance in terms of atoms and what's on each side. Then we're going back to a bit of Chem 1 with this first question. So it is possible to convert but1ene into its structural isomer but2ene. So the type of structural isomerism is shown by but1ene and but2ene. So but1ene is 4 carbons with the first carbon having a double bond. But2ene, the double bond moves to the middle. And the fact the functional group is just moving means this is a position isomer. So positional isomerism. And then we get to our first mechanism. So the first stage in this conversion involves a reaction of hydrogen bromide with but1ene. There it is. Outline a mechanism for this reaction. So remember, outline just means to draw it. It's giving you space to draw it. So first thing to do is draw out all the bonds. So you've got CH3, CH2, CH, then double bond, CH2. So draw all the atoms just to be sure. All the bonds, and it's reacting with HBr, so it reacts with H first because there's a dipole and the H is positively charged. The double bond is an area of negative charge, so that goes out and grabs the hydrogen to form a bond with it. This bond breaks and goes onto the bromine, and what that makes is the carbocation intermediate. So the hydrogen could, just let me draw them in first. It could go onto this carbon or this carbon, which is here or here. And the one it goes on to depends on the stability of the carbocation that should be made. Remember, a primary carbocation, which only has 1 carbon attached to it, is less stable than a secondary carbocation, which has 2 carbons attached to it, which is less stable than a tertiary carbocation, which has 3 carbons attached to it, because the carbons have a positive inductive effect on that positive carbocation carbon, because electrons can be pushed through the covalent bonds. The reason why methyl groups or carbons will have more of a stabilising effect than just a hydrogen is because there are more electrons in a carbon than there is in a hydrogen. So they have more to donate. And so in this case, the hydrogen will go here and the positive charge will go here. And then to finish it off, we have Br-, which must attach to that carbon like that. And you don't need to write the product if it's already given to you. So you get a mark for this arrow, mark for this arrow, a mark for the intermediate, and a mark for this last arrow, and you must have that lone pair and that negative charge in order to get that last mark. And then another mechanism says the second stage is to convert the 2-bromobutane into but2ene. So here, we'll draw that again, so we've got the 2-bromobutane we just made, and it's forming an alkene, so this is going to be elimination, and you've got a choice of hydrogens here to eliminate along with the bromine. So you've got OH-, remember you don't draw the K, it's OH- which is reacting here, the K is just floating around and not doing anything. And so we could take either this hydrogen or this hydrogen, because it has to be a hydrogen on the carbon next to the carbon that has the bromine on. But if you look at the product, the double bond is in the middle. And so therefore it must be this hydrogen that gets taken. And we take that hydrogen, this bond breaks and goes to here, and the bromine leaves by the bonds between the bromine and the carbon breaking. You get a mark for each arrow, but for the first arrow you must have the lone pair and the negative charge on the hydroxide ion. And then we get into section B, which carries quite a lot of marks, and the question's a bit more bulky, but really if you break down the questions, they're just single mark questions, but written with lots of them in one question. So this question is about fermentation. We've got 3 different ways of producing ethanol, or rather it's production of ethanol. Reaction 1 produces 15% aqueous solution of ethanol. It is claimed the reaction produces this way as carbon neutral biofuel. Write an equation reaction 1, so that's your first mark, and name this process, your second mark. Write an equation for the complete combustion of ethanol, that's your third mark, and explain why the ethanol produced in this way might not be carbon neutral. Now, from first look, that will be 1 mark. If you look at the number of marks, there are 5 marks available, so it makes sense there's actually another mark there available. So you just do them in order, no need to write any prose or long-winded answers, just do in order. So write an equation, reaction 1, name the process. Reaction 1 is here, glucose turning into ethanol. And so we've got glucose turning into ethanol. Fermentation, we'll name it first. That's 1 mark. Fermentation is C6H12O6. And it just turns into ethanol with the help of yeast. So C2H5OH plus carbon dioxide. And to balance that, you need 2 carbon dioxides and 2 ethanols. Then we've got to do the complete combustion of ethanol. So we've got C2H5OH. Complete combustion is where it reacts with oxygen to make carbon dioxide and water. So we've got 2 carbons in the ethanol. We've got 3 waters because there's 6 hydrogens in the ethanol. And then to balance the oxygens, we've got 4 there. Another 3 is 7. There's already 1 in the ethanol, so we need 6 from the oxygens. So we need 3 oxygens. And then finally, explain why the ethanol produced by this process may not be a carbon neutral biofuel. And that's because there's going to be carbon dioxide produced somewhere else in this production. So you just got to name a process that will produce carbon dioxide. So transporting, for example, transporting the ethanol will produce carbon dioxide, and that'll be your 2 marks. Again, a longer question. There are 6 marks available here. So we've got 1 mark for the reagent up here. Give a reagent and conditions for reaction 2. We've got name and outline a mechanism. Now the outline will have 2 marks. I'll show you why in a second. And then finally suggest 1 reason other than safety why this method is not used in industry to make ethanol. So that's your last mark. So 6 marks there. So give a reagent first for conditions for reaction 2. So in reaction 2, we are turning a haloalkane into a alcohol. We're substituting the bromine with a hydroxide. So KOH or NaOH is our reagent. The reason why it's not OH- is because a reagent must be something you can pick off the shelf. We can't get a bottle of just OH- signs. There's got to be Ks in there as well. But when we draw a mechanism, we don't draw the K because the K isn't actually reacting. It's got to be there to counter the charge on the OH-, but it's not reacting. The conditions are aqueous for substitution and warm. Now I've said cold in lessons we've had, and that's because it's relatively cold compared to elimination where it has to be ethanolic and hot. But actually you still have to warm it to say 50 degrees to get this to happen, and so in an exam you need to write warm, and I hope I only have to say that in here to help you remember. So that's your 2 marks there. Name and outline mechanism. We've been calling this substitution, but it's actually nucleophilic substitution. And outline means draw. So we've got CH3, CH2Br. So write out or draw out all the bonds. We've got OH- coming in, not the K or the Na if you draw an Na. Lone pair of negative charge, that attacks that carbon, and then the bromine leaves, and that forms your product. No need to draw the product, it's already drawn at the top. And then suggest 1 reason other than safety why this method is not used in industry to make ethanol. Something you can't really revise, but if it's not used, then perhaps there's a low yield. Or maybe slow reaction rate. Those are 2 reasons why it wouldn't be used in industry, because it wouldn't be economically viable. The next question is still about the production of ethanol. So we've got ethene turning into ethanol. So it says identify a suitable catalyst for reaction 3. So this is the hydration of ethene to make ethanol. And we know that, or we should have been taught that we need concentrated either sulfuric or phosphoric, you've probably been taught, phosphoric acid. The word concentrated is really important there. Identify the type of reaction. Well, this is hydration of ethene, so it's a hydration reaction, but also you could have got away with saying it's an addition reaction, because you are adding something across this double bond to make the alcohol. And then give 2 conditions in addition to the presence of a catalyst necessary for reaction to produce a high yield of ethanol. So first we need a high temperature. And you also need a high pressure, but remember this reaction will polymerize the ethene if you have too high a pressure. So you need to state the pressure. So here we need 50 atmospheres of pressure, or 50 megapascals if you wish. So this question is an analytical techniques question. It requires you to match up the infrared spectra with the compounds there, but it tells you to ignore E. It tells you to write the correct letter from A, B, C or D. Some of you wrote E here, which I got a bit annoyed about. So you must read the questions carefully, so we can ignore E in this question. So the first thing to do when you're matching infrared spectra is to look at the compounds you're trying to work out. And what I always do is I look for the functional groups in the compounds. So in each compound there's only one functional group. In this top one here we've got an alcohol OH, which has a peak around 3,300, and an OH peak is often quite rounded at the bottom rather than being spiky. C, cyclohexanone, has a seal bond O, and cyclohexene has a seal bond C. Cyclohexane has no functional group really, so we're going to leave that until last to assign. So if we now look at infrared spectra, the first thing we're going to look for is that seal bond O peak, and that comes at around 1700. So if we look down spectra, this top one has a peak at 1700, but none of the others do. So this top one must be C. I'm then going to look for my alcohol OH peak, and that comes around 3,300, and as I said, it's a bit of a rounded peak. So that is your bottom one here. That is a rounded peak at 3,300, and so that one is B, our alcohol. Then I'm going to look for the functional group seal bond C, which comes at around 1630, and it's not a very big peak either. It's important to realise that peaks that are smaller are also peaks. So if we look down at these last two, we've got a peak here at 1630, and so that one is D, and therefore this one must be A. These peaks here are all CH peaks. If you look at that in your periodic table, your data table, then you'll see that CH comes at around 2,900, 3,000, and so these are your CH peaks there, and there. This next question still requires you to look at these compounds here. So it says a simple chemical test can be used to distinguish between cyclohexane A and cyclohexene D. Give a reagent for this test and say what you observe with each compound. Cyclohexene has a double bond, cyclohexane doesn't, and really should remember from your GCSE work that to test between an alkene and an alkane, we use bromine water, and A you will see no visible change, and with D, the Br2 will decolorize. So it doesn't change colour, it doesn't go clear, it decolorizes or goes colourless, and it's very important that you make that distinction. And it decolorizes because it's got a double bond, and that double bond reacts with the bromine to form a dibromo compound, and it gets rid of that double bond. Then we have this next question, cyclohexanol B can be converted into cyclohexanone C. Give a reagent or combination of reagents can be used for this reaction, state the type of reaction, state the class of alcohols to which cyclohexanol belongs. So we're going from an alcohol to a ketone, so that's an oxidation reaction, and to oxidize an alcohol we need acidified potassium dichromate, and it's very important you say acidified first, and that should say dichromate. Sorry, my writing is pretty poor. And the state of class of alcohols which cyclohexanol belongs. If you can't work it out from the picture, from the formula of cyclohexanol, then just work it out from the fact that a ketone has been made through the this must be a secondary alcohol. Remember, primary alcohols will oxidize to make a aldehyde and then further to make carboxylic acid, but a secondary alcohol will oxidize once to make a ketone. Tertiary alcohol does not oxidize at all. This final question says cyclohexane can be converted into bromocyclohexane by a reaction that is similar to the reaction of methane either with chlorine or bromine. Now this first bit isn't really part of the question because then it asks you to name an outline mechanism for the reaction of methane with bromine to form bromomethane, give one condition, and write an equation for each step of your mechanism. So the name of this mechanism is free radical substitution. We're reacting just an alkane with a halogen. And the first step of this is initiation, and so we're using bromine, and you've got Br2 that's going to make 2 free radical bromines, so 2 Br dot, and this requires UV light, and that is our condition that is needed for the reaction to occur. Then we've got 2 propagation steps as well to write. So our first propagation step is going to make HBr. Remember the Br dot will grab a hydrogen from the reactant to make CH3 dot and HBr, and then you've got CH3 dot reacting with a Br2, and then you'll make CH3Br, your final product, and you'll regenerate your Br dot, and that is all the marks there. So 1 for free radical substitution, 1 for your initiation step, 1 for UV light, and then 1 each for the propagation steps. In this case, you don't need to draw a termination step because it doesn't actually ask you. It doesn't specify which termination step to draw, but if you were to draw one, you wouldn't lose marks. It might be safe to just draw one anyway, and you could react together any 2 of these free radicals in this case because they don't specify a product from your termination step. I hope that helps. Please email me if you have any questions about any of those questions that I've gone through. If you don't understand them,